My pleasure now to welcome our third speaker of the night, Ms. Keena Trowell. Keena is a PhD student in the Department of Mechanical Engineering, working with myself and Professor David Frost. And Keena is going to talk to us tonight about a new type of energy material, or a new type of fuel that's based on metals that can be produced and consumed and recycled without any intrinsic carbon dioxide emissions. Keena.
Every year, humanity uses 500 exajoules of energy. That's a 500 followed by 18 zeros. And that number is only going to go up. And that's a good thing, because it means that life is getting better for people. It's this reliable access to cheap energy that's allowed us in the West to improve our standards of living. In 19th century Europe, when this wasn't the case, life expectancy was about 45 years. Now it's 80. Infant mortality has dropped from 15% to less than 2%. And this map gives us a pretty good idea of where standards of living are pretty good. If they're lit up at night, it means there's reliable access to energy. It also tells us where we need to get more energy. Places like sub-Saharan Africa, parts of South Africa. These are places where sanitation, access to clean drinking water, the necessities of life still lag behind. And so it's clear we need to produce more energy. But the way that we make energy now is through the combustion of fossil fuels, and climate change is real, it's happening, and it's because of the combustion of fossil fuels. So what do we do? On Earth, we have available to us two primary sources of energy: solar and nuclear. Nuclear reactors, of course, but it's also nuclear energy that runs on any geothermal system. And it's also nuclear fusion that runs the sun. But for today, we'll call it another primary energy source. And when I say solar energy, you probably think about solar panels, solar concentrators, of course. But it's also the sun that drives the wind, and it's also the sun that drives our water cycle. So all of our wind and hydro-based energy is really just converted solar energy. We also use solar energy through photosynthesis. So all of the energy we get from biomass, and this includes the food that we eat, as well as fossil fuels, is also just converted solar energy. And so this is what's gotten us into trouble, is that we've literally burned through millions of years of solar energy in just a few decades. And we need to switch to using the solar energy that's available to us in a much smarter way. The good news is that enough solar energy hits the Earth's surface every hour to meet our energy needs for an entire year. And we also have very good technologies for converting that solar energy into electricity. But where there's still a big challenge is in how do we capture that energy so that we can store it for long periods of time and move it over long distances. And so that's the key question. How do we move and store this clean energy in a clean way? Well, we need some sort of new solar fuel, because we can't keep using these fossil fuels. So this is the periodic table of elements. And this is everything that we have available to us in the entire universe. So we need to pick from this. Now, of course, some elements are going to work better than others as a solar fuel. The first criteria is reactivity. The way we get energy out of anything is through a reaction, and this can be a chemical reaction or a combustion reaction. And so we want something that reacts with air or with water and does so at a reasonable rate. So we can't use any of these elements. Because we want to be able to move this energy around pretty conveniently, we don't want anything that's too heavy. So we can't use any of these elements. We don't want anything that's rare, because that's going to get expensive, so we can't use any of these elements. We don't want anything that's toxic or that becomes toxic once it reacts with air or water, so we can't use any of these elements. And then finally, because we don't want our energy system competing with our food system and we need potassium for fertilizer, I'm just going to take that off the list now. So this is what we're left with. And I don't think it's surprising that we see carbon up there, because that's what forms the basis of our fuel system now. And one of the big advantages that these carbon-based fuels offer us is energy density. We can get a lot of energy into a relatively small, light package. So a liter of gasoline has about 45 megajoules of energy. So when you fill your gas tank, you've got about 2,000 megajoules of energy. That's enough energy to run the typical Canadian household for about 2 weeks. So it's quite a bit of energy. But it's the combustion of fossil fuels that's causing climate change, and so we can't really use that. So we'll take that off the list. Another thing you see up here is hydrogen, and you've probably heard about the hydrogen economy, and hydrogen is a clean-burning fuel, and that's true. Hydrogen can be burned in air without releasing any greenhouse gases. The challenge with hydrogen is that it's not very energy dense. So to carry around that same amount of energy, even if you compress that hydrogen into its liquid state, you would still need 5 tanks. So it's not a very convenient way to move energy around. So once we remove carbon and hydrogen, this is it. This is what we're really left with. And you'll see that these things all have something in common, and that is that they're all metals. And in our group, we're looking at all of these. And it's important to think about that we are already using metals as a fuel. So this isn't a new idea, necessarily. So for example, lithium, the lightest metal, is the fuel in a lithium-ion battery, right? So although the lithium itself is very energy dense, you'd only need about 1.5 tanks. Once you use that lithium to make a lithium-ion battery, well, batteries have to carry around all of their reactants and a bunch of infrastructure in order to make them safe and reliable. And so to carry that same amount of energy, you would actually need about 45 tanks worth of lithium-ion battery. Lithium-air batteries are much better in terms of energy density and specific energy that we heard about earlier, but you'd still need about 9 tanks worth of it. So while batteries are very good in some applications, they're great for your phone, for your computer, all the way up to passenger vehicles, these lithium-ion and lithium-air batteries do a really good job, but they're not well suited as a solar fuel. So like I said, our group is looking at all of these metals, and aluminum here has really come out as the front runner in my research. First of all, it's very energy dense. You'd only need about half a tank to carry around that same amount of energy. So I think it's clear what I'm getting at here, right? That I want to use this as the fuel of the future. Now, aluminum is very energy dense, we just saw that, but it's also very common. It's the third most common element in the Earth's crust, so that's good for us. It's also relatively light and inexpensive, and we have really good technologies for processing it and for recycling it. And these processes are just getting cleaner and cleaner, and there's even some promising technology on the horizon that's going to allow us to recycle aluminum without producing any carbon emissions. So there's 2 ways that you can use aluminum as a fuel. The first way is to burn it in air. And when you burn aluminum in air, this can be done without releasing any greenhouse gases. And all of that stored energy is released as heat, the same way that when you burn coal, all of the stored energy is released as heat, and then that heat can be used for something useful like running your power plant. And the other way to use aluminum as a fuel is to react it with water. When you react it with water, about half of the energy is released in the form of heat, and the other half in the form of hydrogen. So you can use that heat directly, and then you can also use that hydrogen directly to feed it into a fuel cell to produce electricity, or you can burn it in air, and again, this can be done without releasing greenhouse gases, and you can use all of that heat for something useful. Now, this aluminum-water reaction is very powerful. That means a lot of energy is released in a very small amount of time, because that oxygen molecule is just ripped right off the hydrogen, or the hydrogen in the water molecule. And a lot of energy is released in a small amount of time. How much energy? It's enough to launch a rocket. So what would an aluminum fuel cycle look like? Well, I like to think about it as the aluminum fuel recycle, because aluminum is so recyclable. So this is how it would work. Wherever it is that you have clean energy, whether that is solar, wind, hydro, what have you, you would use that to process the aluminum. When aluminum is processed, its energy state is increased, so it's effectively storing all of that clean energy. And because of its high energy density, it's a very convenient way to move that energy around. So you can store it for long periods of time and ship it to wherever it is that you need it. When you need that energy, you would react the aluminum with water to release the energy, and then you can use it for whatever you want. And then there's this last step. There's a third reactant in the aluminum water reaction, which is aluminum oxide. And Sarah mentioned this a little bit earlier. This is an inert ceramic solid product. And because it's inert and solid, it's easy to capture and store, and then it can be transported back to wherever it is that you have that clean energy available for recycling. And this is how that loop gets closed. So that's the big picture. Zooming in a little bit, this is what the reaction actually looks like. And in my research, I'm doing these reactions at increased temperatures. Increasing the reaction temperature gives us two benefits. The first one is faster reaction rates. Faster reaction rates just means that the heat in that hydrogen is released quickly, and that's what we need for high power. The second advantage it gives us is that we get increased yields. And what we want is full yield or 100% yield. These are all just different ways of saying more efficient use of the fuel in the system. We want to release all of the hydrogen as possible and leave behind no unoxidized aluminum in the system. And we can achieve full yield. So for example, here around 100 degrees Celsius, we get full yield of this 120 nanometer particle powder. The problem is that nano powders are very fine. So this one, for example, is about 1/50th the size of a human blood cell. It's tiny. And because it's so small, it's also very expensive to produce. And so what we want to do is to be able to go up to larger, coarser particles. But when we do that at these low temperatures, we get very low yields. And this is like having, let's say, filling your gas tank and then 60 to 80% of everything that you put in your gas tank just washes out the other side before you even turn on your car. So in my experiments, to understand this, we need to look at the aluminum at the level of the particle. On the surface of the particle is this aluminum oxide layer. And because aluminum is so reactive in air, this layer forms as soon as aluminum is exposed to air at all. It's a very, very thin layer, and it's a very, very dense layer, and it protects the bulk aluminum underneath. And so this is a really good thing, because what it means is that it's protecting the aluminum beneath from premature oxidation, and this is what's going to allow us to move that aluminum around and store it for long periods of time and not have to worry about, oh, it gets a little wet and then there's a bunch of hydrogen. But it also means that we need to create the right conditions for the reaction to happen. And so the reaction interface isn't at the surface of the particle, but rather it's here, where the bulk aluminum meets the aluminum oxide. So you can think of this aluminum oxide like a fence protecting the aluminum inside it. And so for the reaction to proceed, water needs to get to the other side of the fence. So that's the first step in the reaction, is that the water compromises this surface layer. And this has to be done under the right conditions. It won't happen accidentally necessarily. So this is as if that fence has, there's a bunch of holes in it. And once there's enough holes that are big enough, then the reaction can really proceed. And then this is when you get that fast release of heat and hydrogen. But as that heat and hydrogen is being released, which is what we want, there's also simultaneously a formation of new oxides. So now it's as if that fence has begun repairing itself, and then it's also started to grow taller and taller. Eventually it gets to a point where water can't get to the other side anymore, and the reaction quenches completely. And if this happens before all of the aluminum has been consumed, this is when we get less than 100% yield, and you're left with this aluminum core, which is really just wasted fuel. So in my research, what I'm trying to do is just make sure that water can always get to the other side of that fence. And I'm doing this by increasing the reaction temperature to have the reaction happen in liquid water between 200 and 400 degrees Celsius. And when I say liquid water, this just means that I want the water to not go through a phase change. I don't want it to boil. But you might be thinking, well, water boils at 100 degrees Celsius. And that's true, but it's only true at 1 atmosphere of pressure, which is about the amount of pressure in this room right now. And so if you want to increase the temperature of liquid water, you also need to increase the pressure in the vessel holding that water. So for example, if you wanted 350-degree water, you'd need to go to about 155 atmosphere of pressure, which is about the same amount of pressure you need to crush a car. And the easiest way to do this, to increase the pressure in a vessel, is to put a lid on it. So this is my reactor in my lab with its lid, and it's very well secured to keep that pressure in. And then there's some insulation to direct the heat into the reactor where I want it, and then some instruments to measure temperature and pressure as the experiment proceeds. The other thing about this line is that it ends. And it ends at this point called the critical point. At temperatures and pressures above the critical point of water, water starts behaving very differently. The most interesting thing for me in this case is that things that don't dissolve in regular water can dissolve in supercritical water. Things like metal oxides. And if you remember, it's the formation of these oxides on the surface of the particle that prevent us from always getting full yield. And so the thinking is that in this supercritical water, yes, the oxides will still form, but they won't be very coherent, and they won't adhere to the surface of the particle. And so it's as if, yes, that fence is there, but there's so many holes in it, and it's been so poorly built that it doesn't matter. Water can still get to the other side. So I'll quickly show you some of my data. When I started these experiments, I started with the same 12-micron powder and saw that if I went to a high enough temperature, I got full yield. So naturally, I wanted to go to a larger particle. So this is a 55-micron particle. And we also got full yield once we went to high enough temperatures. So then I wanted to test the largest available metal powder that we have, which is this 108-micron powder. So now we're at about the width of a human hair. And we saw that at 250 degrees, no yield. Nothing happened. It was only once we got to really high temperatures that we got this full yield, and this is in the supercritical regime. So what this early data is telling us is that it is possible to get full yield and high reaction rates in very coarse particles in supercritical water. And so the data that I'm gathering in this work is laying the groundwork for the design of metal water reactors that we can use and actually hook up to a piece of equipment. One of the big advantages of metal water reactions is that they're scalable. And so what we can do is we can design reactors so that they can work for different power applications. So smaller reactors can run maybe a steam turbine and a fuel cell, modified diesel engine, gas turbine engine, all the way up to grid power production. So here, instead of burning coal to run your turbines, what you're doing is that you're taking out the coal combustor and you're replacing that with a metal water reactor and having your power system run off of the products of the metal water reaction instead of coal. Then there's two other things I want to point out here. One is that a lot of engines already exist, right? And so switching to a new fueling system can be an expensive proposition. But metal water reactions, because of the products that they produce, that heat and that hydrogen, a lot of engines can actually be retrofit so that instead of burning fossil fuels, they can be powered off of the products of the metal water reaction. And the second thing is that these applications, these are what we call high power applications. And these are the kind of applications that right now are still heavily reliant on fossil fuels. And these high temperature metal water reactions are one way that we can actually end our relationship with fossil fuels, because this is what's keeping us hanging on, because this is what runs our critical infrastructure. Now, I started out by saying that energy demand is only going to increase, and that that's a good thing, because it means life is getting better for people. For communities to be able to raise a standard of living, they need access to reliable energy so that they can do things like run a sanitation system, clean water system, hospitals, all of the things that make life good and comfortable and convenient. And the good news is that we've got lots of solar energy hitting our planet every hour. The challenge lies in how do we capture this energy, store it, and move it around. And with these high temperature metal water reactions, it's one way that we're going to be able to transition from this world to this world. And this is a world where everybody who wants energy has access to energy, wherever they want it, whenever they want it.
Thank you very much, Keena. Thank you, Keena. So at this time, we can take one or two questions for Keena, and then we'll open it up for questions to the general group. Yes?
Yes.
I'll take. Oh, you've got it. Good. So,
Hamid Zazaidi from Bombardier. I have a question for you, actually. More than 96% of Earth's water is contained in the oceans as salt water. I wanted to specifically address this question. How do you consider this in your study? Does this, because we're not in the sustainability context, we're not gonna put into danger actually those 3.6, let's say, or 4% roughly speaking, in danger. How do you address this? Does this affect the efficiency of the process going on?
Okay.
Thanks.
So that's a really great question. So really it comes down to, here I am talking about sustainability, proposing that we use a bunch of water to make energy. Well, this metal-water reaction actually works better with salt water. That's the short answer. And I mean, of course, in the research at the lab scale, we're using deionized, very, very pure water. But when it comes to deployment, there's already been research done in this area that shows that the salt water actually works better. Well, once we get into supercritical, I mean, this is a little inside baseball, but once we get into supercritical water, it really does a good job of like managing anything that's fed into it. So you might need to filter out particulates and things like that, but when it comes to an actual sort of like chemical removal of salts or anything like that, there's no need. Yeah, great question. Thank you for that.
any other questions?
Well, very compelling story. Yeah, that's a very compelling story, and I get everything in the front end where you're taking clean energy and shipping the source of the energy somewhere. In terms of the recycle, do you think there is a feasible distance where you want to send it out so that you don't have to invest too much energy then bringing the aluminum oxide back to recycle? Is there a feasibility point for the distribution?
Yeah, and I'm sure there would be, and I think that's more of an economic question to me than a science question. But so I look at our energy system now, right? And so, okay, like, where does the natural gas we burn come from? Where did the gasoline that we're burning, where is that coming from? And so, I mean, this is the kind of thing that I think would sort itself out on an economic scale, because we're already doing this with fossil fuels, storing them and then shipping them over great distances. So, you know, it's a matter of figuring out the infrastructure and those tipping points that would make aluminum as a fuel viable or iron as a fuel viable.
Any other questions? For Keena or for any of our other speakers, we could invite you up if there's any other questions. Any last questions, last chance? No? Okay, with that, then we'll thank Keena again for her presentation.
Thank you.
We'll take the clicker.